Good evening and welcome to this fourth installment in Oakland's guide on how to build a data platform. And this is the video series which is accompanying our physical guide to how to build a data platform, which you can find in the description below this video. My name is MLG, and this evening what we're going to walk through is data processing, which some might argue is the most critical decision that you can make when designing your data platform, because you have to make yourself a choice between transactional databases, analytical databases, or the more modern lakehouse. So what I'm going to walk you through today is that decision and why you might choose one of these three or some combination thereof, because this is the critical decision. It will determine how you process your data, and that will inform the architecture that you then go and build and the cloud resources that you pull in to augment the processes that you have. So let's walk through them and take them one at a time. We're going to start with transactional databases, which are extremely well named because in a transactional database, the transaction is God. These are sometimes called OLTP databases, online transaction processing databases, and they are arguably the most simple database that exists, though their function is extremely critical. They are needed when your transactions are vital, and it is vital that they are recorded quickly and they are recorded well. These are sometimes called all or nothing databases, and they are used in things like banking or ticket sales or airline transactions, where what you want is for one transaction to occur, and if at any stage in that transaction something fails, so say a write goes wrong or the power goes down in your data center, then the whole thing can be rolled back. The core precepts in a transactional database can be summed up with the acronym ACID, A-C-I-D, and that stands for atomicity, consistency, integrity, and durability. And the actual meanings of those and what they break down into is slightly beyond the remit of this video, but it's suffice to say that if you have lots and lots of small transactions flying into your database, and it is business critical to you to preserve those transactions in an all or nothing way and to preserve the order in which those transactions are happening, then a transactional database is what you need. So let's just take ourselves a step back for a second and think about transactional databases, because they are arguably the most simple of all the database kinds. The data is organized in rows, and if it comes as news to you that databases can be anything other than row-based, then hold on to your hat, we're going to get onto that later in the video. But we have rows in our database, and each row represents one transaction, and this is where our ACID principles come in that ensure that this data is accurate at all times. Because if you're a bank, say, and each row represents a transaction, when you start writing that transaction, you might have something like an account number and the amount of money coming in, the amount of money going out, where it came from, and so on. And if your database falls over halfway through writing this transaction, then we need this data to be atomic. It's all or nothing, because if we get as far as going, well, here's the account number and here's the amount of money coming in, and then we don't know where it came from because we failed before we could write that down, then that's not acceptable. We need to have atomic transactions. We can only have one thing happening, all or nothing. The technologies that underpin this are, in general, SQL-based. They're things like SQL Server, MySQL, Postgres, stuff like that. And it is no surprise that they are that simple and that they are row-based in the way that they are, because all transactional databases can effectively draw back their lineage to the 50s and 60s and technologies like COBOL, when Grace Hopper and other assorted longbeards at IBM were wandering around and figuring out how data should be processed. A different age. One of wonders and miracles, when silicon ran through our veins and humans walked on the moon, and the problems of git-diff conflicts and node package management were but a twinkle in our eyes. Anyway, transactional databases. They're things you've heard of. SQL is the obvious giant in this field, as we've sort of said. Postgres, MySQL, SQL Server. When you have lots and lots of many small read and writes that you need to keep track of in your business with like millisecond latency, you should be using a transactional database. But MLG, What happens when I don't have many small reads and writes? What I have is honking great massive writes and honking great massive reads that I just need to do sometimes. What if my data science team come to me 3 or 4 times a day and say, I would like 10 terabytes of data, please, to run my machine learning models on top of? Well, in that case, what you're going to need is not a transactional database. You're going to need yourself an analytical database, which has a slightly different architecture underpinning it. Because in an analytical database, and when I'm talking about analytical databases, I'm talking about things like Google BigQuery or Amazon Redshift or Snowflake, you will find that instead of the row being the king, and the way in which we form our data, in general, they're based on columns, because you want to read out one column of data at a time, because in general, your data science team or your analytics team come to you and they say, I'd like all of this column, please, inside the data. So instead of storing our data as rows, we store it as columns, and we can keep those columns in separate places then, and we can break them up and shard them. But what's important is that it's better and more efficient in an analytical database for smaller numbers of big reads and writes rather than many small reads and writes. And if you're interested, by the way, in how column-based file formats work, like Parquet, then we do have a video, I think it's one of the shorts on this channel, that explains how a Parquet file works and how we can use columns to do more efficient data retrieval where your data set is huge. The other thing that happens in an analytical database is that the compute structure is a little bit different. So in a transactional database, we have a server that is associated with a hard drive. So we have a server sitting over here, and we have some hard drive over here, and it is integrated in the way that a computer is integrated with its hard drive, and it sits there and it makes communication with that hard drive and retrieves data out of it. So you put your SQL command into the server, SQL goes in, the server interprets the SQL, it retrieves the data out of its hard drive, and it gives you back data over here, according to whatever SQL query you put in. A similar thing happens in an analytical database. However, instead of having the server communicating with a hard drive, we have that server communicating with cloud object storage. So that's something like Azure Blob or Azure ADLS Gen 2, so Azure Data Lake Storage Gen 2, or an AWS S3 bucket, something like that. And it's worth talking very quickly about how this is different to having a hard drive associated with that server, because ultimately, all the way down, these are just hard drives, okay? And Azure Blob is data stored on a hard drive somewhere. However, what we have done by throwing these objects up into the cloud is we have abstracted away that data management to somebody else. When you put data into Azure Blob or AWS S3, you don't have to do any hard drive management at all. If you have a hard drive yourself, so if you remember our SQL server here had a hard drive associated with it, it has normal hard drive problems that you or I would experience normally, like the laptop that's on your desk has hard drive problems. If you take too many photos of your cat, fill up your hard drive, and you don't have room for anything else, then you have a problem. SQL servers and technology associated with SQL in an transactional database can have similar problems because it has a hard drive right there that could be filled up in theory. The trade-off there is that that hard drive is right next to the server. It's physically integrated with it, so your latency is naff all. However, in an analytical database where we have these huge files, we abstract that storage layer away and say somebody else can deal with that up in the cloud. You can, if you provision yourself an Amazon S3 bucket, so let's just get rid of Azure for a second. If you provision yourself an AWS S3 bucket, you can effectively just keep throwing files in. And AWS deals with all of the problems, like where should this file go? Does it need breaking up into multiple parts and putting on different hard drives because it's just too big and our hard drives are getting too full? What you do is you take your file, You give it to AWS and say, store that for me, please. And AWS go, absolutely, no problem at all. We will do that thing. Here is the address for you to get that file back over a IP call when you need it back. And they deal with all of the nonsense associated with storing really big, really chunky files. It's also, in most cases, less money to put big files up in cloud object storage because you don't have dedicated spinning Rust. You only pay for what you're actually using. You pay for gigabytes of data storage, and it's elastic. They charge you per gigabyte per month. So if you have a data load that is elastic, then you can pay for only what you use. The downside to this is latency. You are making an internet call, you are going out into an external network to get hold of your data and put and retrieve that data. So there is time associated with that call, which you wouldn't have if your hard drive was right next to you. However, analytical workloads are generally so big and so long that the milliseconds of latency it takes for AWS to wake back up and start serving you the bytes from the file that you've requested pales into comparison with the machine learning workload that you're going to do down here. However, the time is here, the time is now. We should talk about lakehouses. We should first talk about the name. Well, let's talk motivation first. What if you want this kind of carry-on, big files, but you'd quite like to be able to use enterprise-grade SQL over the top of them? Well, in that case, what you might need is a reasonably new paradigm called a data lakehouse. And that treats things slightly differently. And that approaches the problem of you having data out here that's being thrown into your blob or AWS S3 storage by other processes, but you want to be able to aggregate that nicely using your compute or your server for your data teams to be able to work on top of. If that's a problem that you're facing, then you need yourself a lakehouse. The lakehouse name comes, rather smugly in my opinion, from the fact that we are taking a data lake and we are combining it with a data warehouse, which is what you would expect this to be. Let's draw out some motivation and come up with an example that will show you why you might consider something like a data lakehouse, because it's easily the most complex of the three examples that we're going to come up with today. If you have an analytical database, that's kind of fine. If you have a transactional database, that's extremely well understood. Lakehouses, they're quite complicated. So let's just talk through why you might want one. So thinking back to our market example and financial services, what if we have cloud storage here and lots and lots of different processes throw in to our cloud storage, lots and lots of different kinds of data with different SLAs, different timescales, different resolutions, hell, different formats. And it's about lots and lots of different things, but I need to be able to aggregate that for my data teams to be able to produce insights that will then ultimately drive value. What on earth do? We get ourselves a lakehouse. So we have our data lake out here. You remember from earlier in the series, a data lake is effectively just like somewhere that we throw data and we worry about transacting it later. Now is the time that we're starting to worry about transacting it and understanding what's going on. So in our example of a financial services company, let's imagine that we have the stock market out here. So we've got stock market data coming in, and that comes in as, I don't know what it might come in as. It just comes in as lots and lots of files, lots and lots of JSON, let's say, which gets updated as new data comes in. That gets thrown into the cloud on a tick-by-tick basis. So anytime the market changes, we get a new change message in some JSON, and that just gets added to the queue and thrown into our data lake. We also have a whole bunch of, let's say, policies. We've got some text out here, which talks about our risk parameters and our tolerance and the regulatory framework that we exist inside, and that gets updated every week. We also have some Excel sheets that come in from one of our analyst teams. We've got some quants out here that produce Excel sheets every day that give us our risk profiles and our tolerance and what other metadata that we're going to need to be able to understand the stock market data that comes in, because we've got machine learning models out here in our compute. So let's call this compute. And here lives our machine learning models that drive decisions that people make over here. What on earth do we do with all of this to make it understandable to this compute here? What we do is give everything metadata. So every little bit of data that's inside here has accompanying it some metadata, which explains what it is, where it is, and how to deal with it. So this JSON here will have some associated metadata with it that says, this is some JSON, this is the resolution, this is how you surface it, this is how you interpret it. This text data will equally have another piece of metadata that explains that it's text data and this is how often it gets refreshed and this is the latest version of it, this, that, and the other. The same happens for this quant data here. We have metadata. This model of surfacing metadata along with the actual data enables our compute to understand what is the most recent version of this data, what should I be getting, and what is relevant to the query that is happening right now. Examples of this technology is something like Google Big Lake or Databricks is built on an architecture that's very much like this. Apache Iceberg is a form of this as well. And in fact, if you're interested in Apache Iceberg, we do have a video in one of the shorts on this channel which explains how Apache Iceberg works and how all of this metadata relates to the data itself and the construction of that metadata which allows the compute to understand what is going on and build those queries. You therefore have yourself a choice. And you don't have to choose one of them. You can choose to blend these methods. If you have a massive data lake like this that you need to make decisions on top of, your data science team might want a lakehouse that allows them to do that. But you might take some of the transactional data inside here and also surface it in a transactional database, because maybe you have account managers and people who have actual money in this that need to know what their account balance is at any given time, like that. And so you have yourself a transactional database that sits on top of some of these flows of money that allows them to access their account. You can mix and match these three approaches. You don't have to pick one of them. Though in general, you should start somewhere and you should start with one of them. But once you're done doing that, you have to think about how you're going to source the compute. This isn't magic. It doesn't come from nowhere. You're going to have to figure out how you're going to source and pay for the compute that runs your database, whether that be regular old SQL Server compute, whether it be like Azure Functions that orchestrate the blob storage that drives your data lake, or it's just the compute that exists inside Databricks that runs your lakehouse. You're going to have to figure out how you're going to pay for it. And that largely comes down to a pretty well understood problem of serverless and on-demand or provisioned access. And the rule of thumb is if you are looking at less than a 30% load on your provisioned access, you should probably consider serverless. But this is a well understood problem and probably not the place to go into that right here. But you should be comparing and contrasting more expensive but on-demand compute in a serverless environment or less expensive but provisioned compute in something that you just guarantee you have access to. Oof, finally, before I go, what we haven't talked about here is a whole load of specialist data architectures. There are things out there like graph databases, which don't have rows and columns at all. They have graphs, not as in the sort of like XY plots that you or I look at and decide whether or not things are going well, but graphs as in connected nodes of data that allow for knowledge to be linked together. There are vector databases, which are becoming increasingly more important as AI uses retrieval augmented generation on top of them. There are lots and lots of small, very specialist database types that you might consider if you have data that requires it. You might think about queue data. If you have real-time data that you need to be able to iterate forwards and backwards on top of and preserve the order of events as they come in, you should think about something like Kafka and its queue data set. But we're not going to go into detail on those right here because you should be choosing between one of the big three: analytical, transactional, or lakehouse. Anyway, if that sounds like your flavor of fun and you want to go into slightly more detail than we have had time to cover here, then you should go ahead and download the Data Platform Guide, which we've written here in Oakland. The link, as I've said at the beginning, is down in the description of the video. I have been MLG, and I shall see you next week when we are going to talk about data ops and automation in your platform.